The universe is approximately 13.8 billion years old, a span of time almost impossible for the human mind to grasp. Despite this immense age, thanks to astronomical observations and physical models, we have been able to reconstruct much of its past history, from the infinitesimally small moments of the Big Bang to the current cosmic structures. However, one fundamental question remains unresolved. What is the future destiny of the universe? Can we truly understand if and how the universe will end? And what would be the consequences of its eventual final fate? When we speak of the destiny of the universe, we are not merely referring to the future of Earth or the Sun, topics we will address separately, but to the overall evolution of the cosmos, encompassing every star, galaxy, planet, and particle in existence. For nearly a century, we have known that the universe is in constant expansion. This groundbreaking discovery is attributed to Edwin Hubble, who in the 1920s observed that galaxies are moving away from one another, suggesting that space itself is stretching. Since then, scientists have pondered the fate of this expansion. 1. Could it continue indefinitely, leading to an increasingly empty, cold, and motionless universe? 2. Could it stop and reverse, resulting in a final collapse? To these two main hypotheses, known respectively as the Big Freeze and the Big Crunch, even more complex scenarios have been added, thanks to new discoveries, such as the Big Rip and speculative theories about a possible cyclic universe composed of infinite expansions and contractions. If the universe's expansion were to continue forever, the effects on the cosmos would be devastating in the long term, over billions and billions of years. 1. Stars would exhaust their fuel, extinguishing themselves and leaving behind white dwarfs, neutron stars, and black holes. 2. Star formation processes would cease, as the gas necessary for the birth of new stars would disperse too much to condense. 3. The universe would progressively cool, approaching absolute zero, the lowest theoretically possible temperature. 4. Even black holes, through the phenomenon of Hawking radiation, would evaporate over time, leaving a dark, cold, and completely lifeless universe. The result would be an eternal cosmic desert, a universe in which no usable energy or dynamic structures remain. If the expansion of the universe were to slow down, stop, and then reverse, the cosmos would head toward an opposite fate, the Big Crunch. In this scenario, 1. Galaxies would stop moving apart and begin to converge under the influence of gravity. 2. Matter would compress into increasingly smaller spaces, causing density and temperature to rise. 3. Ultimately, all matter and energy would concentrate in a single point, similar to the Big Bang, forming a gravitational singularity. Some theories suggest that such a collapse could trigger a new Big Bang, giving rise to an infinite cycle of expansions and contractions, known as a cyclic universe. However, the extreme conditions of a singularity are difficult to describe with our current physical laws. The scenarios do not end here. Dark energy, a mysterious force that appears to be accelerating the expansion of the universe, introduces additional possibilities. 1. Big Rip. If dark energy continues to accelerate expansion at exponential rates, a moment could come when the forces that hold galaxies, stars, and even atoms together are overcome. 1. The universe would be torn apart until it completely disintegrates. 2. Collapse induced by dark energy. In some models, dark energy could change over time, slowing and reversing the expansion, leading to a collapse even in a seemingly flat universe. 3. Sudden transitions. Some models hypothesize that dark energy could undergo sudden changes, causing catastrophic events such as the instantaneous dissolution of space and time. A crucial element for understanding the universe's future is its average density. If the density were greater than a critical value, gravity would stop the expansion, leading to collapse. If it were less than the critical value, expansion would continue forever. And if it were exactly equal to the critical value, expansion would slow without ever fully stopping. Current observations indicate that the universe's density is very close to the critical value, making its fate difficult to predict with certainty. Another determining factor is dark energy. If it represents a cosmological constant, a fixed value associated with empty space, then accelerated expansion will continue forever, leading to the Big Freeze. However, if the behavior of dark energy changes over time, entirely new scenarios could emerge. Despite the uncertainties, the current cosmological model suggests that the universe will continue to expand forever at an increasing rate, heading toward a big freeze. However, this final fate is so far in the future, billions and billions of years, that it far exceeds our temporal scale. For now, what we know is that the universe still holds extraordinary mysteries, many of which could be unveiled by future scientific discoveries. Stay tuned as we continue to explore the secrets of the cosmos and understand our place within it.